general relativity step by step. Last time I defined the number flux vector n in terms of the 4 velocity u, and I'm going to spend a little bit of time developing what these terms mean here. So what I've got is a coordinate system here, and I'm just suppressing several of the dimensions. I'm going to have x and t, and I'm going to have world lines of my particles in green like this, cruising up there. Now what I'm going to do is ask, well, where are these particles going? What are they doing? And I'm going to draw a line here, which is a surface. It's a line here, but of course I've got 2 extra dimensions, which in fact, it's not even a surface. I'm going to put that in scare quotes. It's more like a 3 surface, because I've got 4 dimensions, time, x, y, z, and what I'm doing is I'm fixing x, and so I've got time and y and z, which are varying. So I've got a 3-dimensional thing, a 3-dimensional manifold left over. But I'm just going to call it a surface, and remember that this isn't a perfect word. And I'm going to ask, what is the particle flux through this surface? Well, the answer to that is, let me just write it down, and then I'll unpack it. This u here is the speed in the x direction, which is just this component of the 3 velocity here. So that's where that comes from. This thing here is the rest particle density. And this thing here is, of course, the Lorentz contraction term. Because, of course, in the rest density, the particles have got a different density from the density that I perceive because they're moving relative to me. So that's 1 over root 1 minus beta squared. And similarly, the flux through the other directions is going to be gamma n u v and gamma n w. Well, that's great. So these are the fluxes. I guess you could specify per unit area, per unit time, if you really wanted. Well, that's great, and that really explains this term, and this term, the 3 space components of the number flux vector. This one here is a little bit more problematic. Actually, it isn't more problematic, but it's a little bit difficult to describe it in terms that make sense for us slow-moving creatures who don't move quickly relative to the speed of light. It makes sense. You see, here I've just casually created a surface. Well, I'm going to get rid of that. I'm going to get rid of that, and I'm going to draw a new surface. Go back to black, and I'm going to draw a new surface. This is t equals constant, and in the same way, I've got particle flux through this surface. I had particle flux through a surface with constant x. Now I've got a surface, a scare quotes surface of constant t. And I'll ask, what's the flux? And again in scare quotes, because flux doesn't really do the meaning of the word isn't quite right. And again in scare quotes, through, and again in scare quotes, the surface of constant t. That's these lines. That's how many of these world lines go through a little unit area. Of course, it's not area; it's a volume. Well, the answer to that is just n gamma, because that's the density as I perceive them. Because the surface of constant t is just a volume of space at a constant time. There it is. It's just a line here, but of course I've got y and z as well. So it's just n gamma, which equals the density as perceived by me. Okay, so there it is. So the four flux n, the number flux n, is just n gamma u, n gamma v, n gamma w, and that's a nice 4 vector. A nice 4 vector which transforms nicely. Actually, last time I said that in the next screencast I'd show you something astonishing. I've not really shown you anything too astonishing here. I'm going to defer that to the next one because I don't want these screencasts to be too long. So I'm going to stop there, but what I want you to pick up is the interpretation of these elements of the number flux vector, which is the flux of particles through three surfaces defined orthogonal to the four three surfaces orthogonal to each of the four coordinate axes. So I'm going to stop there. Stop.